Hello students and welcome. In this video we're going to go over section 3.1 on basic concepts of probability and counting. We will also look at some homework problems from this section. Let's go ahead and begin on page 130 where it says probability experiments. And it says when weather forecasters say that there is a 90% chance of rain, or a physician says there is a 35% chance for a successful surgery, they are stating the likelihood or probability that a specific event will occur. In the preceding chapter, you learned about the role of the descriptive branch of statistics. The second branch, which is inferential statistics, has probability as its foundation, so it is necessary to learn about probability before proceeding. So in other words, in chapter 2, we talked about descriptive statistics, so we learned how to summarize data with tables and graphs, and numerical summaries such as the mean, median, and standard deviation. So the other part of statistics is called inferential statistics. And like it says, right, before we can study inferential statistics, we have to have a good grasp of probability. So what is probability? So probability is the study of random phenomena and how we quantify the likelihood of random events. So some examples of random phenomena include the outcome of a coin toss. So in this picture here, you see the two sides of a Washington quarter. So on the front side is George Washington's profile, and then on the reverse side is a depiction of an event in George Washington's life called the crossing of the Delaware. In any case, when you toss any coin, right, it'll either come up heads or tails. And what makes the coin toss random is that you don't know the outcome in advance. So for example, when you toss a coin, you don't really know whether it's going to come up heads or tails until it lands on either the front side or the back side. Another random phenomenon is rolling a six-sided die. So a die is in the shape of a cube, and on each face is a certain number of dots. So when you roll a six-sided die, you do not know the outcome in advance, but when it does land, right, it'll either be a number 1 through 6. Some other examples of random phenomena are the weather forecast for the next 2 days. So even though we can predict the weather with a certain level of certainty, again, we don't know what the weather will be like exactly in the next day or next 2 days. So that's why it's a random event. Another example are the two teams who will make it to the World Series at the end of baseball season. So baseball season will begin in the next month. So once again, we don't know which teams will be in the World Series. So that's why it's considered a random event. Okay, let's go back to this section. So as you go through the section, it's a good idea to write down the definitions of the key terms here. So in the middle of the page, you'll see 4 key terms. So let's go over those. So a probability experiment is an action or trial through which specific results are obtained. So the result of a single trial in a probability experiment is an outcome. Okay, we talked about some examples of probability experiments. The set of all possible outcomes of a probability experiment is called the sample space. And an event is a subset of the outcomes in the sample space. Okay, so an event may consist of one or more outcomes from the sample space. So an example of a probability experiment is rolling a six-sided die. So the possible outcomes of a die toss, right, are the whole numbers 1 through 6. So this is our sample space. An example of an event that you can consider when rolling a six-sided die is if you roll an even number. Okay, so an even number would be a 2, 4, or 6. So the event of rolling an even number consists of the 3 outcomes, 2, 4, or 6. However, when you roll a six-sided die once, you can only get one outcome. Okay, so for example, if you roll a six-sided die, the outcome may be a 2. Okay, so let's go ahead and take a look at some examples from the homework. So this is question 1 in section 3.1. And the problem says a restaurant offers a $12 dinner special that has 4 choices for an appetizer, 10 choices for an entree, and 3 choices for a dessert. And the question is, how many different meals are available when you select an appetizer, an entree, and a dessert? So to answer a question like this, we're going to use what's called the fundamental counting principle. And the fundamental counting principle is described on page 132. And it says that if one event can occur in m ways, and a second event can occur in n ways, then the number of ways that the two events can occur in sequence is m multiplied by n. So in other words, what it says to do is that you take the number of ways that the first event can occur and multiply it by the number of ways that the second event can occur, and that's the total number of ways that the two events can occur in sequence. This rule can be extended to any number of events occurring in sequence, so we can use the fundamental counting principle for 3 or more events that occur in sequence. Okay, let's go ahead and go back to the problem. Okay, so once again, we have 4 choices for an appetizer, 10 choices for an entree, and then 3 choices for a dessert. So we're assuming that we're choosing the appetizer first, followed by the entree, and then followed by the dessert. So in other words, the choices we're making are occurring in sequence, so one followed by the other. So the fundamental counting principle says that we multiply the number of ways for each choice. So four choices for the appetizer, so that's 4. Okay, multiply that by 10 choices for the entree. And then followed by the 3 possibilities for the dessert. So when we multiply those 3 numbers together, we get the total number of meal combinations that are possible, so we get 120. So with the different choices for each part of the meal, right, there are 120 different combinations. The next question says, a realtor uses a lockbox to store the keys to a house that is for sale. And it says that the access code for the lockbox consists of 4 digits. So the first digit cannot be a 2, and the last digit must be even. And the question is, how many different codes are available? So once again, we're going to use the fundamental counting principle to determine the number of different codes that are available for this lockbox. So this is an example of a lockbox. So it's a little container in which you can store like a set of keys or something else. And the only way to open the lockbox is with the correct code. Okay, so going back to the problem, it tells us that the first digit cannot be a 2, okay, and the last digit must be even. All right, and it doesn't say anything about the middle 2 digits, right? It doesn't say anything about any restrictions on the middle 2 digits. So whenever we work with a lockbox or some other kind of combination, usually the digits we have to work with are 0 through 9. So if you count them individually, you'll see that there are 10 digits, 0 through 9. Okay, so we know that the first digit cannot be a 2. So if we can't select a 2 for the first digit of the combination, right, we can kind of cross that off of our list. And like that. The question is, right, then how many digits do we have to choose from the remaining digits? Okay, so other than 2, right, there are 1, 2, 3, 4, 5, 6, 7, 8, 9. So there are 9 possibilities for the first digit. Right, so in other words, as we answer the question, right, how many possibilities do we have for each number in the combination to the lockbox? Okay, so for the first digit, it's 9 possibilities. Okay, so how about for the second digit? Okay, well, since there are no restrictions on the second digit, according to the problem, right, we can choose any of the 10 digits above. And so there are 10 possibilities for the second digit, and then same for the third digit, so there are no restrictions on the third digit of the lockbox. What about that last digit? What did it say about the last digit? Okay, so according to the problem, it said that the last digit must be an even number, and in the note here says that 0 is considered an even number. So remember, even numbers are like 0, 2, 4, 6, and 8. So here we can include the 2 in the last number of our lockbox. Okay, so the even numbers are 1, 2, 3, 4, 5. So there are 5 even digits that we can choose from for that last number there. Okay, and according to the fundamental counting principle, to get the total number of codes that are possible with this lockbox, okay, we're going to multiply the number of digits we can choose from for each number. Okay, so it's 9 times 10 times 10 times 5. Okay, and we get 4,500 combinations possible. Let's go ahead and take a look at the next question. Okay, so question 3 says, assuming that no questions are left unanswered, in how many ways can a 5-question quiz with 4 multiple choice questions be answered? So I'll go ahead and let you answer that on your own. Okay, so for each of the 5 questions, right, how many answer choices are possible? So whatever it is, and it tells you here, right, multiply that number by itself for the number of questions that there are. Yeah, so that's how you can approach number 3. Okay, let's go ahead and take a look at number 4. Problem 4 says a company is conducting a survey to determine how prepared people are for a long-term power outage, natural disaster, or terrorist attack. The frequency distribution on the right shows the results. Use the table to answer the following question, and the question is, what is the probability that the next person surveyed is very prepared? So let's see how we can approach this question. So this notation, so P parentheses E close parentheses, is used to mean the probability of event E, where E is some event of interest to us. Okay, so to get the probability of an event E, right, we take the number of ways that E can occur and then divide that by the total number of possibilities. So when we look at our table, the event that's of interest to us is a person who is very prepared for the power outage, a natural disaster, or a terrorist attack. So according to our table, there are 241 people that are very prepared. And if we add up all the numbers in the table, we can get the total number of people that were in the survey. So I'm going to go ahead and do that off camera. Okay, so the total number of people in the table was 2195. So we're going to take the ones that are very prepared, which is 241, and divide that by 2195 to get the probability. So rounded to 3 decimal places, the probability is 0.110.